Okay, here's part 3 to the mini lecture on estimators, and this has the theme of goodness. In part 1, I think it was, we said there were 2 questions we wanted to address. One of them was, if we have an estimator, how do we know how good it is? And that's where we talked about the mean square error of an estimator. Here, for goodness, we want to talk about the other question, is this. How do we find a good estimator? All right, and so, of course, what we're estimating is a parameter. The last part, previous part, talked about how we measure the mean square error, and that gives us a measurement of goodness. But if we have a parameter and we want to figure out the best way, the goodest way to measure it, how do we do that? So I'm going to talk about maximum likelihood estimates. So what's a way we can choose an estimate that maximizes our likelihood that it's a good estimator? So here's an example based on something the book does, and I'm going to make it slightly different. So consider a random variable x that's distributed as a binomial where n is 20, but we don't know what p is. So this random variable has 2 parameters, and one is set and we know what it is, but what's the best way to estimate the second? So what's the best way to estimate the second, or to find an estimator? So you can't estimate without making an observation. So one of the first things you got to do is make an observation. So that means x is a random variable, so let's just see what value it would give us after an experiment. And so let's take the possibility that x is 4, right? Our x is a binomial where the number of Bernoulli trials is 20 with probability of success p, so it's possible we could have 4 successes. So given this, what's a good or a reasonable estimate for p, having no other information? So before we proceed, I want to remind ourselves of a couple things, or at least one thing. So if you look at the probability mass function, which is the probability that a random variable equals a value x, we have a formula for that for the binomial, and it's 20 choose x times p to the x times 1 minus p to the 20 minus x. So we observed x equals 4. So what we observed had a probability p of 4, right? That's the probability x equals 4. And that, according to our formula, has that probability. Now, remember, we don't know what p is. The question we're asking is what value of p makes x equals 4 the most likely? right? That's our one observation of x. What makes it the most likely for us to have seen? So we'll look at two ways to answer this question. So the first way is by using the expected value of x. Remember, the expected value of x is the most likely outcome. Of x. So it's reasonable for us to assume that if we saw the outcome x equals 4, right, we can say that was the most likely outcome, x equals 4. And we'll look at the consequences of that assumption. The second approach we'll take is the most likely outcome occurs at a mode of the distribution, a global maximum. That has shades of calculus 1 in fact. And if you think it back to when we talked about probability distributions and think about the graph of a probability distribution, the most likely occurrence is where that graph is the highest, right? That's where the probability is concentrated. So that's our approach for number 2. Okay. So let's take approach 1. On the one hand, the expected value of our random variable is a binomial random variable of with parameters n and p, and the expected value of such a random variable is n times p. In our case, n is 20, so I can write this. On the other hand, the output that we saw was 4, and since the expected value is something we're most likely to see, it makes sense for us to say, well, that would be 4. So put these two things together and say 4 equals 20p. Well, divide both sides by 20. And so my estimator would be 4 over 20, which is 0.2, 1 over 5. So from this approach, using the expected value as a expected likelihood output, we would say that in this case our estimator of p would be 0.2. Now let's look at the other approach, approach 2, which is calculus based. In this case, we have this. X is a binomial random variable, n equals 20, and we don't know what p is. What we can say is the probability that we have x as an outcome is given by this formula. 20 choose x is p to the x times 1 minus p to the 20 minus x. So we're going to define this function f of x p, which is this thing here. Look at both x and p as variables. We have observed x equals 4, so in the case when x equals 4, our function is 20 choose 4, p to the 4 times 1 minus p to the 16. So this is our probability distribution. So this is the function that associates the probability of x equals 4 with the various values of p. And we want to figure out what p maximizes this value. So in Calc 1, we know that we can take this function here, regard it as a function in P. It's a nice polynomial in P. So we can take its derivative, set it equal to 0, solve for P, and we'll find out where the maximum is. And let's do that. So I'm going to call this 2a. And we're going to take the derivative with respect to P of f of 4p. So looking at this is a constant, so I can pull that out to the front. And then differentiating this, I've got two functions here in P's. I need to use the product rule. And so it tells me the derivative of the first, which is 4 times p cubed, times the second, plus the first, times the derivative of the second. Oh, and the second, there's a chain rule. So we got to do that. That's the derivative. So let's simplify that. Looking at it, you'll see that there's a p to a power and p to a power. And it looks like there's a p cubed I could pull out of everything. And here we've got a 1 minus p to a power and a 1 minus p to a power. And I could pull out a power of 15 on that. So I can rewrite this whole thing as 20 choose 4 times p cubed times 1 minus p to the 15. And then I'm left with 4 times 1 minus p plus 16p. Right, that's going to be a minus 16p. And we'll simplify what's in that last group. 4 times 1 minus p minus 16p looks like it's 4 minus 20p. Okay, that's good. So that's the expression for my derivative. Now, we'll use calculus and say, let's set that equal to 0 if I think critical point. So the whole thing, the whole product equals 0 if and only if one of the factors equals 0. So the first factor here is when the probability equals 0. That's not interesting to us. Or the probability equals 1. That's not interesting to us either. Right? Those are kind of trivial. Those aren't even random variables then. And so we're left with this last thing. So this is the interesting thing. This derivative equals 0 when that equals 0. So solve that for p, and you get p equals 4 over 20, or 0.2. Now, notice, we saw that before. The fact that taking an analytic approach using calculus gives us the same answer that using expected values gives us should tell you something. Should make you feel good about things we've talked about so far this semester. But now I'm going to show you something else. So let's take a step deeper into the calculus waters. I'm going to give you a little theorem here. So here's a theorem. It says that if f of x is a differentiable increasing function with a continuous derivative and if x equals c is a local maxima of g of x, then x equals c is a local maxima of the composition. That is to say, this theorem here tells us that composition with a monotonically increasing function preserves local maxima. So why is this true? We'll just keep this short and sweet. Well, if you look at the derivative of this composition function, the chain rule tells us that's the product of the derivatives. And if at x equals c this is 0, then this whole thing is 0. So that tells you that x equals c could be a local maxima. But since f is increasing, f prime is positive. So a positive number times the derivative here being 0 means that, and the fact that the derivative is continuous means that if this changes a little bit, then the derivative is still going to be positive. And the first derivative test tells you that a local maxima occurs when a function goes up and then goes down. So the derivative of this to the left of c, the derivative is positive. To the right of c, the derivative is negative. But in the neighborhood of c, this is always positive, so it doesn't change the sign of our derivative. So to the left of c, this is positive. To the right of c, this is negative. So this is why this theorem is true. That if you compose a function with an increasing function, monotonically increasing function, then that composition is going to preserve local maxima. So why is this important? So here's the corollary. If f of x is a likelihood function, with a local max at x naught equals p naught, then the log of f of x has a local max at the same point. Okay, because the logarithm function is a monotonically increasing function. So why is this important to us? Well, you come back to the previous page, and we have this likelihood function here. And we want to maximize p to find the maximum likelihood. Okay, so let's copy this over and do this. So we're going to copy this up here. So let's take the log, the natural log of this. That's the log of 20 choose 4, p to the 4th, 1 minus p to the 16th. So using the properties of logarithms, the logarithm of the product is the sum of the logarithms. So we can write that. And also, logarithms do cool things with exponents. So by properties of logarithms, this exponent comes down as a coefficient. So I can say this is 4 times the property of log p, and this is 16 times the property of 1, or log 1 minus p. This corollary says the maxima of this function are the same as the maxima of this function. So we're going to take the derivative of this and set it equal to 0 and differentiate with respect to p because that's our variable. So the derivative of this constant is 0. The derivative of this is 4 over p, and the derivative of the last term is 16 over 1 minus p, and then we got to put that minus 1 there for the chain rule. So we get 4 over p minus 16 over 1 minus p. Now we're going to want to set that equal to 0 and solve. So let's simplify this. Finding a common denominator. We get that. And looking at the numerator, we get 4 minus 4p minus 20p is 4 minus 4p minus 16p is 4 minus 20p. All over that. So we want to set that equal to 0 and solve. So I'm moving to the next page. 0 equals 4 minus 20p over p times 1 minus p. Multiply both sides by the denominator. We clear it. We get that. And solve for p. You get this, which is, no surprise, 0.2. It's what we got from the previous approach. And it's what we got from our first approach with the expected value. So three ways to give you a sense for how we can find a maximum likelihood estimator. So I'll do one last example here. And it's going to use the Poisson random variable. So let's suppose we got a random variable x that's distributed as a Poisson random variable with parameter lambda. And so we're going to ask, how can we use an observation of this random variable to give a good or a maximum likelihood estimator for our lambda, so lambda hat. What we need to remember is this. So I'm going to write down here the probability mass function in this way. Normally we don't put that x in there. But the probability, our random variable equals x, is given by this formula. This is the probability mass function. Okay. So for any positive counting number, the probability that our Poisson random variable equals that positive counting number is given by this. Okay. We don't really consider any other possible output. So using the logarithmic approach, let's define g of lambda to be the natural logarithm of this function. And logarithms are not defined when the input is 0, so we're confined to looking at this. So we have the natural logarithm of e to the minus lambda of lambda to the x factorial. And then now using properties of the logarithm, we say this is the same thing as the logarithm of e to the minus lambda plus the logarithm of lambda to the x minus the logarithm of x factorial. Working this out further, we can take this exponent down to be in coefficient, like I just wrote. Same thing in the next term. And in the last term, the factorial is the product of descending values of x. You take the logarithm of a product, you get the sum of the elements. So we're going to say that this is the sum of the log of i's as I goes from 1 to n. Now, what's the derivative with respect to lambda of g lambda? Well, in the first term here, log e is just 1. So when we take the derivative of the first term, we get a minus 1. In the second term, x is a constant with respect to lambda, so we get x over lambda, because the derivative log of lambda is 1 over lambda. And this last set of things here, there's no lambda, so that's just going to be 0. So this is our derivative. Set it equal to 0. And let's solve for lambda. And we get lambda equals x. So we say that given an observation of a random variable, our maximum likelihood estimator is going to be that value. Right? And that's the example. Thanks for watching.